So today we're going to talk about moles, molar mass, and isotopes in chemistry. Something you're going to use throughout AP chemistry. It's very important you understand this. So moles is simply a measurement of an element. So 6.022 times 10 to the 23rd atoms, that is equal to 1 mole of an element. Now, because different elements have different weights, because they're bigger or smaller atoms, they they don't they don't correlate to each other 1 to 1 when you try to go grams to grams. So when we write chemical equations, you're going to have coefficients and you're going to have subscripts within your chemical equations, and those are going to tell you how much moles of an element exist in that equation. And this lets us equate different elements to each other and make conversions and make observations in chemical equations. This will be very important when we move on down the line. But for right now, what you really need to understand is how this 1 mole is derived. We'll show where it comes from, and then what information you can use starting today just by looking at the periodic table from knowing this. So right here we have a box. This will represent a box on the periodic table, and it'll look something. Oh, sorry about that. It'll look something like this. So you'll have three things here. You have your elements abbreviation. So this would just be the element that's in question. You have your atomic number. This represents how many protons are in one atom. The number of protons within an atom is what determines what element it is. So these they determine each other. If you have something with 4 protons in it, it would not be worth it. And then this final number you'll see down here is the molar mass. And this is always measured in grams. So the molar mass represents how much the element weighs with 1 mole. So how much the element weighs for 6.022 times 10 to the 23rd atoms of that element. This number right here, Avogadro's number, you might hear your professors call it, isn't as important as it seems. It is important when you're making conversions between moles to atoms or moles to particles, but you really don't need to worry too much about this number for right now. What you need to understand is how we get to molar mass, and that the atomic number determines the element. So how moles were derived is 1 mole is equal to 1 mole is the number of atoms that have to be added up. The number of protons that have to be added up to equal 1 gram. So 1 gram per proton. So when you are given a sample, sometimes you'll be asked questions like you'll get lithium 7, and this is what it'll look like. And they're going to ask you um, how many protons are in this element, how many neutrons, how many electrons, and you want to be able to determine this, and we can do this by just looking at this right here. So because there's nothing in this top left corner when you see something like this, minus or plus, we don't have that here. We know that it is evenly charged, so we don't need to worry about the electrons versus protons right now. From this, we get this is the molar mass of the element, and we know that lithium, because it's lithium, has 3 protons. So we know that 3 grams of this molar mass must come from protons based on this relation right here. So we know this has 3 protons, and this must have 4 grams of mass come from somewhere else. So the two other things that make them atoms, which I'm going to describe later in more detail in another video, is you're going to have your neutrons and your electrons. Electrons are so small, they have almost no mass. So we can pretty much make them negligible when we're taking um, like a single element. They're so small that no one really measures them in chemistry. So that means the other mass must come from neutrons. And neutrons are also 1 gram per neutron in a mole. So because we know this is lithium, so it has to have 3 protons, 3 of the grams must come from protons, and the other 4 grams must come from neutrons. So we can tell that this thing has 3 protons and 4 neutrons within the atom, and that's how we get this number right here, which represents the molar mass. Now you may be wondering why this molar mass right here, 7, is different than the molar mass provided here in the box. And that is because of something called isotopes. Isotopes are basically how the element actually exists. So an atom can have half of a proton or half of a neutron, and that's where it gets all its mass from. So all its mass, when we measure in moles, has to actually be a whole number. But if you look at the periodic table, this doesn't make sense because all of our molar masses are decimals. And that is because this molar mass right here is actually the average mass of all the isotopes. If you know anything about statistics, you know that the larger sample size you take, the closer you get to the true average. And because 1 mole is such a large number, it's 6.022 times 10 to the 23rd, so large of a number, I don't even know what you would call it. Since it's such a large number, we can treat the average as the true value. Because when you take a large enough sample size in statistics, you get closer to the value being you get closer to your average being the true value. So what you need to understand is not a lithium, a lithium 7 is what I should say, is an isotope, and this represents one atom. An isotope represents one atom. But so it'll have its own molar mass. It has to be a whole number because of how the mole to mass ratio works. But in practice, when you take such a large sample size and there are different isotopes that occur, like lithium, there's lithium 6 and lithium 7. Because these two different ones occur, the average then is how we get 6.94 as our average mass. So how would you, let me ask this a different way. One of the AP questions you get on a test is you'll get a graph and you'll get something that looks like this, and it'll be an isotope graph. And over here will be the percent of, I think they call it abundance on the test. So it's the percent of the atom abundance. So how often it occurs, percent of occurrence, just to make it simpler. They'll call it percent of abundance. I'm pretty sure different chemists use different names, and I'm pretty sure that's a terminology it gets used. And down here, it'll be ranked by molar mass, and it'll make this bar chart. So let's say we're doing lithium. So this is going to be the lithium percent of abundance by molar mass. So there are two options for lithium. There's lithium 6 and lithium 7. And they'll have peaks on them, which will correspond, just like reading a graph, over to values on the side. And then these values, they'll kind of be rounded, and they're looking for a guesstimation using this graph of the molar mass. Now we know the molar mass is 6.94, but we're going to tell you how you can show this math on a test that you might get from your teacher or on quick AP tests so that you can prove that why this is the molar mass and make sure you get those points. So lithium 6, lithium 6, so lithium with a molar mass of 6 has a 7.4% of abundance, and lithium 7 has a 92.6% of abundance. I shouldn't have drawn these last series for sig figs. We're not going to worry about those right now. I'm going to do a whole separate video on sig figs later. So what you're going to want to do is you're going to want to find out the true molar mass, which is going to be the average of these two isotopes and their percent of abundance. This is actually really simple math. All you're going to do is take the molar mass, so 6, and you're going to multiply by the percent in a fraction form. So that just means move the decimal places 2 to the right. Multiply by the percent of abundance in decimal form, not percentage form. So you just move it to the right, and you're going to do your multiplication. And then when you add these numbers together, you're going to get something close to the molar mass here. And you can actually just write the molar mass that you know, because as long as you show these steps right here of breaking down into percent of abundance and then multiplying it in decimal form and then adding them together, you're going to get all the points that you're looking to get on the AP test and in your class, because this is what they're looking for. Your teacher knows and the AP graders know that you know this number. They want to know that you know where it's derived from and how you get it. They want to make sure you understand that in practice, it's not just lithium floating around with this mass. It's different atoms of lithium, different isotopes of lithium floating around with different masses, but because we live in such a large world compared to how small atoms are, we can practice the real average, which is the molar mass. Unless you're specifically given questions that target isotopes and target things like that, you're going to be able to treat isotopes, or sorry, you're going to be able to treat isotopes as kind of forgettable. You're going to be able to use the molar mass as the real mass that you use for all your equations because it's such a large sample size that we talked about before. So let's do a brief recap. Recap. The things you need to know. Avogadro's number is how we get our moles, and this is how many atoms exist in 1 mole, and 1 mole of protons equals 1 gram of protons and neutrons, I should say. So this is going to be important when we talk about being able to find um, the different components of elements and things like that. But what you need to understand is this is a mole measurement right here. This is the relationship of 1 mole to protons and neutrons. That's where this number actually comes from. And then we can use these large sample size to use real, oh, that's a terrible cut. We can use this such large sample size to find real isotopes and their percent of abundance and find the average mass of the isotopes, and that is our molar mass. And this is what we're going to treat as our mass of lithium or any element. We're going to treat its molar mass as its mass because we exist in a large, large world, much larger than atoms. And until you get to the very small scaled down world, you don't have to worry about isotopes. That's when you get to nuclear engineering and nuclear fission and things like that.